Today we're going to start a new topic, the last topic of this term, and the main theory section of this module, which is called optimization. So optimization is all about minimizing functions and multiple variables. And believe it or not, this is has incredibly wide applications to optimizing the track of a spacecraft, to starting weather forecasts, to optimizing the position of electronics on your mobile phone. So although in essence it seems quite a stark problem, it has a lot of applications. Okay, and we're going to start off by doing 1D problems, so-called line searches, and then we'll finish off with 2D optimization at the end of this term. Okay, so I want to start by going back to the slides we have right at the introductory lecture about motivating all these different methods, and we talked about motivating numerical methods, but we also talked about this separate thing called optimization. Now, a very short translation of optimization is about minimization or maximization of functions. Now that might sound from a calculus viewpoint as a rather sort of rudimentary, sort of maybe a bit dull sort of process in calculus, but it turns out that if you can express your problem in terms of a function that needs minimizing or maximizing, then this becomes very powerful, and it becomes a very useful basis of data science and all sorts of real life problems. And I listed these are listed in the lecture notes, some examples of optimization problems. Not all of these are going to be covered in this part of the module, but it just gives you an idea about how sort of central optimization is as a topic to solving real-world problems with mathematics and numerical methods. So a traveling salesman problem was about, if you have a list of cities and the distance between each pair of cities, what is the shortest possible route that visits each city exactly once? It's called a traveling salesman problem, and it's a kind of classic problem in computer science to test an optimization method. There's optimal distribution of components on a circuit board, which are very relevant to designing your mobile phones. There's starting numerical weather forecasts, which is a potentially very difficult problem. You've got lots of different data sources. You have satellites, weather balloons, and you have a weather model, a big computational model that tries to wind forward the partial differential equations for weather forecasting. But so somehow you need to synthesize all that information to get a starting point, an initial condition for a weather forecast. And that is actually done by trying to construct almost quadratic or robustly quadratic function that you minimize, a so-called cost function. So this is the type of problem that we're going to be type of optimization problem we're going to be dealing with in this part of the module. It's one way you can make your complicated problem synthesized into a single cost function. It's a cost function of many different variables, but as long as you've got that cost function, you can then start to minimize it. And we want to just construct iterative methods of minimizing such cost functions. Our final one is finding an ideal spacecraft trajectory. Getting from Earth to Mars, say, and all of these are sort of optimization problems. And it's a very big topic, and we just tackle one aspect, and that's this sort of sometimes called single objective optimization. It's basically about minimizing a cost function. And we want to do that in a sort of iterative way. Okay, so let me just close that slide down. And so in this module we have we'll have two types. We'll consider 1D and 2D, and by implication of 2D, many dimensions. So the 1D minimizations, sometimes also called line searches, we're going to compare two methods, one that's an improvement on the other. The first one is called dichotomous search, so we'll start looking at that today. And then the second is called golden section search. And the idea about 1D is all about, it's a little bit like your bisection method. So it has there are analogues of that earlier on in the course, about trying to basically, if that's your minimum there of a 1D function, it's how, starting with these two endpoints here, how can we zoom in to the minimum in an iterative way? And the dichotomous and the golden section search are two very closely related methods that do that. Okay, so that's the first one, is this just minimization of a 1D function. We know that we can't minimize any otherwise. And then the second part, it's a bigger part, is 2D minimization. I.e. minimizing f of x or y. But the key thing here is that these methods also apply to many dimensions, and that's really where they come into their own. The reason we're sticking with 2D is because it's the easiest context to, it's the smallest number of dimensions you can understand how these methods work. The two methods we'll come across are gradient descent and conjugate gradient descent. And again, they're a pair. You may notice that this is my or our method of teaching you different numerical methods. Often is to introduce a pair, one that maybe is more efficient than the other, and then what we can learn by doing that. And there's no change here in that sense with these two methods. So once we got to conjugate gradient descent, we've got the end of term, right? And then you can give yourself a big pat on the back for getting to the end of term. And there's also some theory we need to set up before we get to these methods about whether the existence. So if I just put existence of minimum, and how we can prove that. Oh, that's too many I's. That's a sort of another topic that just comes before then. Okay, so this is, I suspect, is completely new, but as you say, the line search stuff relates a bit to the root finding part of the module, and gradient descent and conjugate gradient descent. Well, that will relate to vector calculus, which I can't remember whether you do it this term or next term, but you will do it sometime this year. In the second year, varies each year which term you do it actually. There's some things that carry over to there, so that it's not, although it's new, it's not unrelated to anything you've done. Okay, so let's start with line searches. Get myself organized here. Okay, so here's some slides because there's some diagrams here and I want that. So first of all, we're going to start off with a dichotomous search. So this is quite a busy diagram. So let's label what's going on. And I think this is a diagram. So this is in the lecture notes. This is figure 5.1, page 57. Okay, so exactly that diagram, and this is how we do it. And the first thing to notice is it is very like bisection because we just defined Ci is the bisector at any point, and I is the step of algorithm. So this is the ith step, and this is the next step, I plus 1 step. Okay, some people present these lines the other way around. They might start at the top and work down the bottom. It doesn't matter really at all. The key point is we're doing a line search. So if you just look at the bottom line, we're starting with an initial bracket, if you like, AI and BI. We construct the bisector. We're not looking for the minimum, we're not looking for the root this time, as we did with the bisection method before. We're now looking for the minimum. A slightly different problem. And what we want to do is we construct a bisector. We want to figure out whether is the root, so we're having to find this bisector CI, is the root here, is the root going to be in here, the left hand part of the bracket or the right hand part of the bracket. Okay, and in this case we've just constructed that it's going to be in the left hand bracket. So what we've done is we look at the function, so this is a key assessment, we see where the function is less on which side. So we construct a small relative to the width of the domain, a little epsilon, and we look at either side, CI plus epsilon this side, CI minus epsilon that side. So the dichotomy is this aspect of, shall I go this side, shall I go that side? So when you're in a dichotomy, in other words, one other way it's used in English I've come across anyway, is that when you're not decided about which way to go, either side. So that's why it's called dichotomous search. In a way it's quite helpful method name because it tells us a bit about how the method works. You remember that's the most helpful type of method. So it's a dichotomy, so we look either side, we go have a look at CI epsilon one side, epsilon the other, and we pick epsilon at the beginning. And if the function is less, so remember we're looking for the minimum here. So if the function is less on the CI minus epsilon side compared to CI plus epsilon, we select the left bracket. So we reject Now you may notice that I've constructed a new bracket based on CI plus epsilon. Now there is slight variation out there about how this method is implemented, whether you use CI or CI plus epsilon. Of course, if epsilon is small, it doesn't matter. But I think it's more rigorous to choose CI plus epsilon because there's a very small chance the minimum could lie in this little gap between CI and CI plus epsilon. So that's why I've constructed it like this, and that's what for exam questions and everything, stick with my method of doing it, my choice of brackets. Okay, I think there's so in this case we select it, so we convince ourselves the minimum, and then we repeat. So we've got the new A value, which is exactly the same as AI, and BI plus 1 is just this one here, and then we have our new bisector. That's another bisector there, yeah. By the way, don't be afraid to do this with it. You maybe just print out a section of your notes and a diagram and scroll all over it, trying to indicate that you understand how it works and to notate it, because this is quite a useful thing. Equally with code. Just print it off and annotate it, and if you don't understand, come to me and I'll try and help explain. Okay, so so that's essentially all there is to it. You construct a bisector, you see if the function is less one side or right, where you have this small change epsilon, and then you construct the new bracket and then repeat, and so on and so forth. So let's just write So let's go on section search. We're not onto that yet. So let's just, with that diagram in mind, let's just write out what the algorithm is for dichotomous search to complete this. So we aim is to find the minimum of f of x. So it's a one-dimensional function. So we have given bracket AI bi, we construct bisector. So another way of looking at it is an adapted bisection method for finding minima, and it's just AI plus BI divided by 2. Then we construct a small distance epsilon, which you have to define at the beginning of your algorithm, either side of CI. So I'll use the board, and then we have the decision stage, if you like, will correspond to an if test. So if f c minus epsilon, so epsilon left hand side of it is less than f of ci plus epsilon, then the minimum must lie to the left in interval AI, ci plus epsilon. So that was exactly the diagram that we saw before. Let's just go to that if we can. I'll tell you what, let's just go to the diagram. So if f of ci minus epsilon is less than fca, we have to select the new bracket is ai and ci plus epsilon. If it's the other way around, if f of ci minus epsilon is greater than f of ci plus epsilon, then minimum is to the right in interval ci minus epsilon comma bi. Let's draw a diagram. So we've got AI, BI, that's our bracket. Along comes our bisector, CI, and we have CI minus epsilon, CI plus epsilon. And we've decided now, actually, the function is greater on this side than on this side, so the minimum's got to be on the right. So we discard this part of the domain. So the new domain then is just going to, sorry, new interval is going to be bi ci minus epsilon. Okay. And that's our first optimization method. So in the practical, I think we try and look at code of this type of problem as well to give it its practical basis. But I hope you can see actually the methodology is very similar to bisection. It's just we've introduced this epsilon, and and the decision making is based on your function rather than your intermediate value theorem, which is what you did before. But it's the same sort of principle. So we also expect when we come to assess this method that it will have similar rate of convergence. See. Okay, so I've used up my time for this video. So next time I'll do a worked example of this by hand. Okay. See you next time.